Welcome to this crucial session on a topic that sits at the very heart of modern, reliable systems: automating infrastructure integrity checks with SRE principles. In today's rapidly evolving digital landscape, where systems are complex, distributed, and constantly changing, ensuring the integrity of your infrastructure is paramount. Any deviation from a desired state, whether malicious or accidental, can lead to outages, security breaches, and significant financial losses. This lesson will equip you with the knowledge and strategies to proactively safeguard your systems. Over the next 10 minutes, we will explore why automation is not just beneficial but essential, delve into core SRE principles that guide this automation, examine practical tools and techniques for implementation, and discuss best practices to build resilient, self-healing infrastructure. Get ready to transform your approach to infrastructure management. At its core, infrastructure integrity refers to the state where your entire infrastructure, from hardware to software configurations, consistently matches its intended, desired, and validated state. This isn't just about whether a server is up or down. It's about whether its operating system version is correct, if all required patches are applied, if network configurations adhere to security policies, and if application dependencies are correctly provisioned. A deviation, even a minor one, could be a misconfiguration that degrades performance, a missing security patch that creates a vulnerability, or an unauthorized change that compromises data. Ensuring integrity means having confidence that your infrastructure performs predictably and securely, aligning perfectly with your architectural blueprints and compliance requirements. It's the bedrock upon which reliability, security, and performance are built. The necessity of automation and infrastructure integrity checks cannot be overstated, especially when you consider the scale and complexity of modern systems. Manually checking every server, every configuration file, and every network rule across hundreds or thousands of instances is not only impractical, but frankly, impossible. Manual processes are notoriously prone to human error, leading to missed updates, overlooked vulnerabilities, and inconsistent deployments. Furthermore, they are incredibly time-consuming, diverting valuable engineering resources from innovation to tedious, repetitive tasks. Automated checks, on the other hand, provide continuous, consistent, and rapid verification. They can scan your entire environment in minutes, identify deviations instantly, and even initiate self-healing actions. This shift from reactive, labor-intensive remediation to proactive, automated validation is crucial for maintaining high availability and security, ultimately saving significant operational costs and reducing mean time to recovery. Site Reliability Engineering, or SRE, provides a robust framework that perfectly aligns with the goals of automated integrity checks. 3 core SRE principles are particularly relevant here. First, embracing risk and error budgets means understanding that 100% reliability is often unattainable and uneconomical. Instead, we define acceptable levels of unreliability through service-level objectives and use an error budget to guide development and operations. Integrity checks help ensure we don't spend our error budget on preventable misconfigurations. Second, reducing toil is about minimizing repetitive, manual operational work. Automating integrity checks directly addresses toil by replacing manual audits with programmatic scans. Third, measuring everything underscores the importance of data. We must monitor the outcomes of our integrity checks, track deviations, and use these metrics to continuously improve our automation and overall system health. By integrating these SRE principles, our integrity automation becomes strategic, focused on reliability, and continuously improving. The landscape of tools for automating infrastructure integrity checks is vast and constantly evolving, but they generally fall into several key categories. Configuration management tools like Ansible, Puppet, and Chef are fundamental. They define the desired state of your infrastructure as code and enforce it, automatically correcting deviations. Infrastructure as Code (IAC) platforms such as Terraform and CloudFormation allow you to provision and manage your infrastructure in a declarative manner, ensuring that the deployed state matches the defined code. Compliance and security scanning tools, including various vulnerability scanners and compliance frameworks, analyze configurations and dependencies against security benchmarks and regulatory requirements. Monitoring and alerting systems like Prometheus, Grafana, and ELK Stack play a crucial role by continuously observing the system and notifying teams when integrity breaches occur. Finally, policy as code tools like Open Policy Agent, OPA, allow you to codify and enforce organizational policies across your entire stack. The strategic combination of these tool categories forms a powerful defense against integrity drifts. Designing effective integrity checks requires a thoughtful approach, focusing on what truly matters for your system's reliability and security. First, prioritize checks based on criticality. Which components, if compromised, would have the most severe impact? Start with foundational elements like operating system configurations, network firewall rules, and critical application dependencies. Second, define desired state with precision. This means having clear version control definitions for every configuration item, ideally as code. For instance, SSH port 22 only from specific IPs, or specific Docker image tag v1.2.3 deployed. Third, consider different types of checks. Configuration drift detection identifies changes from the desired state, vulnerability scans look for known security flaws, and compliance audits verify adherence to standards like PCI DSS or GDPR. Finally, ensure your checks are granular enough to provide actionable insights, but not so verbose that they generate excessive noise. A well-designed check should immediately pinpoint the problem and often suggest a solution, allowing for efficient remediation. Bringing automated integrity checks into your operational workflow demands seamless integration with your existing CI/CD pipelines and monitoring infrastructure. For instance, during the continuous integration phase, configuration files and IAC templates should undergo static analysis and linting to catch syntax errors or policy violations before deployment. In the continuous deployment CD phase, after infrastructure is provisioned or updated, automated checks should immediately run post-deployment validation. This shift-left approach means catching issues earlier, making them cheaper and faster to fix. Beyond the pipeline, continuous monitoring is essential. Background services should constantly scan your running environment for configuration drift, comparing the actual state against the desired state defined in your version control system. These checks should be scheduled periodically, perhaps hourly or daily, and leverage your existing monitoring stack to collect metrics and trigger alerts. Remember, the goal is not just to find problems, but to do so efficiently and proactively, preventing issues from impacting users. Detecting an integrity breach is only half the battle. Responding effectively and efficiently is equally critical. The moment a deviation is identified, your automated system should trigger alerts and notifications through appropriate channels, think Slack, PagerDuty, or email, ensuring the right teams are immediately informed. These alerts must be clear, actionable, and contain all necessary context, such as host, web server-01, detected with unauthorized SSH key on /SSH/authorized keys at 10:30 a.m. UTC. Following the alert, the ideal scenario involves automated remediation. For minor, well-understood deviations, this could mean automatically rolling back a configuration change, restarting a service, or reapplying the desired state using configuration management tools. However, for more complex or critical breaches, manual intervention with guided playbooks might be necessary. This involves human operators following predefined, documented steps to investigate, confirm, and resolve the issue. Always ensure logging and auditing of all detected breaches and remediation actions, both automated and manual, to facilitate post-incident reviews and continuous improvement, tracking metrics like mean time to restore (MTTR). To truly succeed with automated integrity checks, it's vital to adhere to best practices and be aware of common pitfalls. A key best practice is to treat infrastructure as code religiously. All desired states, configurations, and policies should be version-controlled, testable, and reviewable, just like application code. This provides a single source of truth and enables reproducibility. Another practice is to start small and iterate. Don't try to automate everything at once. Begin with the most critical components and gradually expand your coverage. A common pitfall is alert fatigue, where too many non-actionable alerts desensitize teams. Ensure alerts are high fidelity and represent genuine problems. Also, avoid over-reliance on single tools. A layered approach using multiple tools for different check types offers more robust coverage. Finally, always foster a culture of continuous improvement. Regularly review your checks, learn from incidents, and refine your automation strategies. This iterative process ensures your integrity checks remain effective and relevant as your infrastructure evolves, helping to keep your system stable and secure. In conclusion, automating infrastructure integrity checks guided by SRE principles is no longer a luxury, but a fundamental necessity for any organization striving for highly reliable, secure, and efficient operations. We've explored how understanding infrastructure integrity, embracing automation to reduce toil, leveraging SRE principles like error budgets, and utilizing a robust set of tools can transform your operational posture. The journey involves meticulous design of checks, seamless integration into CI/CD, and a well-defined response strategy for breaches. Looking ahead, the future of infrastructure integrity will likely be shaped by even more advanced automation. Expect to see greater integration of AI and machine learning for anomaly detection, predicting potential drifts before they occur, and enabling truly proactive self-healing systems that not only detect but automatically correct a wider range of integrity issues with minimal human intervention. Continuous innovation in this space will empower teams to focus even more on strategic initiatives rather than reactive firefighting, ushering in an era of unprecedented operational stability. Thank you for joining this session.